And you can see that that's really what's happening, because, so for example, outside this region, say for example, if you didn't know the fields here, you see you couldn't calculate what happens there. So as this moves in, you see you get to this particular surface. You might say, well, why isn't it the outgoing light cones from here? And the reason is just that to know what happens here, for example, you'd need to know what happens here as well. So the question of what is the Cauchy development of what region is something which is important. And that is the opposite, if you like, of the question that was asked at the end of the previous lecture, which was, what can you actually observe? Well, suppose, for example, you had a surface that looked like that, and you were capable of looking at what happened in that region. There would be a surface of some other value of constant time. Then, of course, you could retrodict everything in this region, and this would be the d minus of sigma. But you would, of course, be capable of observing things. Well, this is the region that would influence you if you were sitting there. So thinking about the Cauchy development of something is an important issue when it comes to thinking about the causal structure of black holes, or indeed any other space-time. So let's now look at black holes. Let's look at the Kruskal coordinates again. For the Schwarzschild metric. I remind you that the line element was ds squared is equal to minus e to the minus r over 2m du dv divided by r plus r squared into d theta squared plus sine squared theta d phi squared. And we that the region U negative, V positive, it was exterior to the black hole. So if we try to construct a Penrose diagram for the Schwarzschild space-time, then of course infinity looks exactly like it does in Minkowski space. So we can start over here, and we know that there's going to be a nice scry plus and scry minus, and a time like past and future infinity. But we also know that the surface U equals 0 or the surface V equals 0 are null surfaces. And these correspond to the black hole and white hole horizons that we found earlier. So, where do they lie? Well, they will actually lie in this diagram, something like this. And if you think about it, V goes up in that direction, and U goes up in that direction. So this is the surface U equals 0, this is the surface V equals 0. So this horizon, again, see, if I draw the light cones here, because light cones always lie at 45 degrees to the horizontal or vertical, you can see that this is a region which, if you're inside here, you're trapped. You can't get out from here to here because that would violate causality. It would make you move in a space-like fashion. Similarly here, it's exactly the opposite. Here, if you're in this region, you can't avoid moving out in that direction. If we draw lines of constant r in this picture, this is Schwarzschild r, then these lines would look something like this. So r going to infinity would be out here, and then r equals 2m will be the limit of this surface. Similarly, if we did lines of constant t, then they would look something like this. T equals 0 would be here, but as you move towards the future, then you can see that this surface, t is getting very, very large and tending to infinity, and that would encompass both Scri+ and the black hole horizon. But if you look at this metric, there's nothing stopping you going through u equals 0, and r will continue to decrease. And you will eventually reach the singularity, which is a space-like surface. So this surface here is r equals 0. If we draw lines of constant r inside the black hole, well, this is r equals 0. So r being constant looks something like this and tends to 2m here. You'll notice that here, trajectories of r equals constant are time-like, but here they're space-like. There's nothing wrong with the original Schwarzschild type metric. Let's put it up here. Once you're inside r equals 2m, it's just that it doesn't give you correct information about what happens at r equals 2m. But the whole situation, as you know, is time reversal invariant, so I could have gone the other way and done this. I would find a singularity in the past as well. And again, if you're interested in lines of constant r, well, they will look something like this. This region here, if you draw lines of constant t in from here, then they would look something like this. And then the same thing down here. So what that tells you is that a knowledge of t and r using the Schwarzschild metric, I mean, it could be in this place or that place and it wouldn't make any difference. Same values of t and r appear here and here. T equals minus infinity there. If you wanted to be continuous, then of course you could make t equals plus infinity there. But you can see there's obviously something missing because this surface is isometric to that surface, so there is a second asymptotically flat region sitting here. You might worry about this because you might say, well, does that mean that if I've got an asymptotically flat region here with a black hole in it and apparently a white hole, what about this region? Can I ever explore it? And the answer is no. You cannot move from this region to this region in a causal fashion. You can only move from here to here in a space-like fashion. So you could say, well, if I want to have a space-like motion like that, you could, but it's not something which is physically reasonable. But if you look at what happens at, say, it's the easiest way to do it. If you fix t and theta equals pi by 2, then the induced metric on that surface is going to be dr squared over 1 minus 2m over r plus r squared d phi squared. And this looks like some kind of cylinder. So if you just draw a picture of what this looks like, then it looks something like this. So this is where the radius is looking like r. So r is large out here. And although there is coordinate singularity at r equals 2m here, it's easy to get rid of it. You can have a d rho is equal to dr over the square root of 1 minus 2m over r. And you could integrate that up and find rho as a function of r, and then that will give you something nice. What you'll discover is that this region has a minimal cross-section at r equals 2m. And then it will start to grow again. There's nothing stopping you extending through that region, so it looks something like that. So that's what the geometry of the region which takes you from there to there. Of course, I've drawn this as a circle. It's really an S2. So this is sometimes called a wormhole. But fortunately for us, it's an untraversable wormhole. It's not something that you can actually play with directly. Well, that's the Schwarzschild metric for you, for m positive. There is, of course, m was a constant of integration. So you might ask yourself, what happens if m was negative? Well, then there'll be no zero of 1 minus 2m over r. It will simply, nothing strange will happen until you get to r equals 0. It's still singular. But you'll see that R0 is time-like. So what is the Penrose diagram of that? Well, far from R equals 0, R equals infinity, it's going to have a perfectly well-defined asymptotic region with a well-defined scri plus, scri minus, and space-like infinity. And indeed past and future time-like infinity. However, at r equals 0, you know it's singular. So the space-time looks like that. So this is going to be the singularity. This is a prototype of what is usually called a naked singularity. The reason it's called naked is because if you were, say, sitting at scri plus, say here, and you were looking with your telescope along a past null ray, you'd be able to see the singularity. From the point of view of classical physics, this is something of a disaster. Let's suppose that we are classical physicists. We think the singularity is real, not somehow modified by quantum mechanics. And you ask yourself, I want to do some kind of prediction. So I'm going to construct a surface here and ask, from the knowledge of fields and their first derivatives in the time-like direction, what can I deduce? Can I see everything in this space-time, or what? Well, the answer is the Cauchy development of this surface is this region. So if this is surface sigma, then that's the development of sigma. It means in this region you can't tell what to do. The reason you can't tell what to do is that you would have to put boundary conditions at the singularity in order to be able to predict what happens in this region. That's not what you expect to happen in physics. Physics usually want to be able to say, in a space-time that looks like this, you'd be able to think, well, surely I should be able to predict what happens here. The answer is no. Unless you put some kind of boundary conditions on the singularity, you can't construct the Cauchy development. That's why it's generally said that singularities cause, at least naked singularities, cause a loss of predictability. Now let's go back and look at the Schwarzschild metric sitting up there. If you look at the remote past, you'll see that there is a singularity in the past, although it's a space-like singularity, and that will influence what happens in either of those two asymptotic regions. So that too gives rise to a form of non-predictability unless you have some kind of boundary conditions at the singularity. So the Schwarzschild metric contains a naked singularity. This property is not unique to Schwarzschild. The Friedman, Robertson, Walker universes have the same kind of issue with singularities in their past. And indeed, many other cosmological metrics have a similar problem. I will leave that for Roberto to discuss, but we will talk about realistic black hole metrics in a bit. So that's the Schwarzschild metric. Are there any other black hole metrics? Well, it turns out that you can extend the idea of black hole metrics in asymptotically flat spacetimes in two directions, or even both at once. Let's do the easy one first. There is a series of metrics known as the Reisner-Nordstrom metrics. They have a line element, ds squared is minus 1 minus 2m over r, plus q squared over r squared, dt squared, plus the same thing to the minus 1 dr squared, plus r squared into d theta squared plus sine squared theta d phi squared. There is, associated with this, an electromagnetic field with a 0 is equal to q over r, and that's it. And then the energy momentum tensor is the usual one, FAC FBC minus a quarter GAB FCD FCD, and I believe with my conventions a factor of a half out here. Now obviously the behavior of this function is similar, but does have some striking differences to what happens in Schwarzschild. Instead of having a single zero at r equals 2m, you'll see that there are two zeros at values of r which we can calculate. So there are really three separate cases. One, modulus of q is less than m. Then that function has two zeros. At r equals r plus and r equals r minus, and the values of this is at r plus minus is equal to m plus or minus m squared minus q squared. Case 2, modulus of q equals m. Then there is a single degenerate zero, it's a double zero if you like, at just at r equals m. And lastly, there's a possibility that modulus of q is greater than m, in which case this thing has no real zeros. In each case, you can calculate the Kretschmann scalar, and you'll discover that r equals 0 is a curvature singularity. So is the geometry anything like the previous geometries? And the answer is maybe. This one is an example of a naked singularity, and its Penrose diagram is identical to Schwarzschild with negative mass. Now let's look at case 1. Case 1 is, the first thing to notice is that if you go through the Eddington-Finkelstein or Kruskal constructions, you'll discover that the surfaces r plus and minus are null surfaces. So without going through an enormous calculation, I'll just show you what you get. Be warned that this picture is infinite in both directions vertically. So that's why I'm making this picture a little small. So this is an asymptotic region, so here would be a scri plus and a scri minus. And this surface here would be r equals r plus, that one, and that one. But then if you go through the calculation of analogous to the Kruskal calculation, you can find detailed instructions on how to do this in Brandon Carter's lecture notes in 1972 Les Houches Summer School. He will tell you exactly how you do this construction. I don't want to do it because it will take too long. So you'll discover inside r equals r plus, there's another surface here where this would be r equals r minus. And if you go through that surface, you'll end up at r equals 0, where now r equals 0 is a time-like singularity. But now the trouble with this is that this really goes on forever, because suppose you were here. You could go that way or you could go that way. So you will discover that there's a mirror image of this region here. Then here, you discover there's a mirror image of this region. And then you see, but that's just the same as this, but time reversed. So you'll be able to construct another asymptotically flat region here and here. So these are asymptotically flat, so I'll call this scri plus and scri minus. But you could have gone backwards in time, as well as forwards in time, and you get a picture that looks like this. Now, at some point, this gets impossible to draw. Well, I think it has got impossible to draw, isn't it? Well, just suffice it to say it goes on like this forever. Well, of course, this picture is well liked by science fiction aficionados because they say, well, if you were here, you could move to a different asymptotically flat region here by moving along a time-like trajectory and managing to avoid the singularity. So that looks like some recipe for a very exciting form of space travel, but I don't recommend it. Let me tell you why I don't recommend it. This surface, r equals r minus, is perturbatively unstable. What does that mean? It means, suppose, for example, I construct a spaceship here. It will have some energy momentum tensor. And I ask, what does conservation of energy and momentum mean as I move along this red line? And the answer is, it means it will blow up at this surface. So the energy momentum tensor for whatever you construct moving along the red line blows up at r equals r minus. And if that happens, you would expect this thing to become singular. But I'll put that in inverted commas and add a question mark because you don't really know that. What that would lead you to conclude is that in a realistic example of constructing a black hole, you wouldn't expect anything to the future of this surface. Can I prove that? No. It's just a general expectation of what you might find. So that's what happens with the Rice-Norton metric in case 1. Now let's look at case 2. So case 2, modulus of Q is equal to M. In this particular case, you see that of course no sort of region like R equals R minus. So if we construct the original asymptotic region, then I'll discover that this surface here, R equals M, is what's sometimes called a degenerate horizon. And you'll just discover a time-like singularity sitting inside that looks something like that. If I go through the business of constructing lines of constant R here, they will look something like this. That they don't change as you go through that surface. If you go in the other direction, you can construct I'm not sure I did that right. Let's do that again. If you go in this direction, you will find the analog of the wormhole. So this is except in this particular case, it's a bottomless pit rather than a wormhole. It doesn't take you to any other asymptotic region. It's a sort of bottomless pit. It just goes on forever. But again, fortunately, to get there, you'd have to go in a space-like fashion, and you can't really go in a space-like fashion. And so this bottomless pit isn't going to bother you. So that is, roughly speaking, the nature of the Reisner-Nordstrom metrics. There is Sorry? Yeah, I get the impression I've done something not quite right with this picture, actually. Let me try again. The asymptotic region looks like that. There is an internal, the singularity goes there. No, it really is not right. The singularity does go there, it goes there, does that. And then this is another asymptotically flat region. I'm never going to get this right. I'll leave that as an exercise. I have a picture in my notes, but it doesn't look anything like what I was just trying to draw. There is something peculiar about these extreme Reisner-Nordstrom black holes, and that is to say that they are supersymmetric. What that means is, in general, curvature will break supersymmetry. What that means is that typically there is, for supersymmetry not to be broken, there is an equation of this form, where this is some particular form of covariant derivative, but it will involve not just the usual connection, but also terms involving the other fields of supergravity. And this is a spinor. So in the case of Einstein-Maxwell, this operator turns out to be the usual covariant derivative on spinors plus 1/4 of FBC gamma BC gamma A. And you can see that if you do this in dimension 4, there's an issue here, because what have you got here? You've got 16 equations, and 4 unknowns for epsilon. Gamma is the usual Dirac gamma matrix. Constructed in the space-time. So that means that gamma A anticommutated with gamma B is equal to 2 times GAB. Does that answer the question? Gamma BC. Oh, gamma BC. Does that help? So usually you can't solve this equation. But in the case of extreme Rice-Nordstrom, you can. And that tells you that supersymmetry, or at least some fraction of possible supersymmetry, if there is any, is not broken. This has a very interesting consequence, because that's behind the concept of the Papa-Petru-Majumdar metrics. These are metrics of the following form: ds squared is equal to. Now, see if I can get this right. This just means dx squared plus dy squared plus dz squared. A0 is equal to 1 over v. And v is equal to 1 plus. The sum from I is 1 to n of mi over the modulus of x minus xi. So what this represents, so this is just this bit, it's Cartesian R3. So if you draw a picture of it, this object V has got poles at various places, absolutely anywhere you like. Each pole represents a extreme black hole with charge equal to the mass. So another way of saying this is that the gravitational attraction of the masses is equal to the electrostatic repulsion of the charges. And you can just put them anywhere you like. Of course, this metric is singular at x equals xi, but it's just a coordinate singularity. So here is exercise number 2. Take the example when n is equal to 1 and find the coordinate transformation that takes you to the original Reissner-Nordstrom coordinates that we wrote down somewhere up there. Is that the only thing that you can do? Well, the answer is no. We all know that you can have Kerr black holes, because after all, those are the ones that have been found. The problem with Kerr black holes is that the Kerr metric is rather complicated. This satisfies the field equations RAB is equal to 0, and the line element in what's usually called Boyer-Lindquist coordinates is equal to. Now this is not something which I can ever manage to remember. Rho squared into. And rho squared is r squared plus a squared cos squared theta. Delta is r squared minus 2mr plus a squared. So these coordinates are usually called Boyer-Lindquist coordinates. The Kerr metric dates from 1963, which is, of course, a long way from 1916. Again, you can see that there are going to be 3 cases, because this function here might or might not have 0, 1, or 2 zeros. So again, there are cases 1, 2, and 3. Case 1, well, let's see. Delta is 0 at r equals r plus or minus. R plus or minus is m plus or minus m squared minus a squared. So either the zeros are distinct, they're the same, or they're complex, in which case they don't really happen. So that gives you 3 separate cases. coincident zeros. No zeros, no real zeros at any rate. In this formula, there are two integration constants, m and a. M we can interpret as the mass of something. A we should call some kind of rotational parameter. If we ask ourselves about the killing vectors of this metric, there are two. There's d by dt, reflecting the fact that the thing is stationary. D by d phi, reflecting the fact that the thing is axisymmetric. So we've broken spherical symmetry when it comes to this particular metric. Kerr did not find the metric in this form, but in a rather simpler form that is, well, different. So he found it in essentially what are known as, well, essentially at the analogue of Eddington-Finkelstein coordinates. So this is a rather more complicated thing. In particular, it's complicated because you've got cross terms between t and phi here. But, nevertheless, if you just send r to infinity, you'll see that the metric tends to Minkowski space. And so, the kind of technology that we've been looking at can be reused for this particular metric. Let's look at case 1 now. Did this... Yes, fortunately that did happen. That one wants to go up. Penrose's diagram for Kerr is almost the same as that for Reissner-Nordstrom. The only difference is that you get some new regions here beyond the singularity. So it looks like this. If you analyze the thing carefully, you'll discover that out here, space-time is asymptotically flat. But, of course, contains a singularity. But now the singularity isn't quite the same as it was in Schwarzschild, and that's because spherical symmetry has been dropped. If you compute the Kretschmann scalar, then this is equal to 48m squared over rho to the 6th, which is 48m squared over r squared plus a squared cos squared theta cubed. And so to have something singular, both r equals 0 and theta equals pi by 2 at the same time. So that tells you that the singularity is of the form of a ring in the equatorial plane. To see it really is a ring, you need to look at the metric close to r equals 0 and theta equals pi by 2, but you will discover that what you think of as a radius depends on how you actually get to the ring. So this is kind of a nasty place. There is, however, a further complication with this region that exists close to here, to the right of the singularities. I've drawn it there. So this region is a region in which g phi phi is negative. That's kind of bad. If you look at the metric up there, you can see that that's certainly something which can happen, because you can see that there's a minus sign sitting in front of the r squared plus a squared, the minus sign sitting in front of the minus delta a squared sine to the fourth d phi squared term, coming from just up there, the last term in the expression. That's bad because if you could fix r t theta and send phi to phi plus 2 pi, then you'll end up at the same place that you started from, but you will have moved in a time-like direction. So this is an example of causality violation. And such behavior is thought to be unphysical. I don't think any of us are qualified to say whether or not it is unphysical, but it's generally thought that it's not something which happens. Again, we don't need to worry about it. And the reason is that, again, the inner horizon, r equals r minus, is perturbatively unstable. And therefore, in practice, if you threw something in and tried to reach this region, starting from here, well, you could, but to exploit this, you'd have to have gone through r minus, and r minus is unstable, so that would be something which is not advisable. Is that it? Well, the answer is not quite. There is one last family of black holes, and you can, of course, guess what it is. There's nothing stopping you having the Kerr metric, but electrifying that as well, in which case the differences are small. We don't need to do very much to find the analog. So Kerr-Newman metric not RAB equals 0 anymore, it's Einstein-Maxwell. And the only difference is that delta changes to r squared minus 2mr plus a squared minus q squared. And that means that this formula will change to m squared minus a squared minus q squared, and everything else stays the same. So again, there are two Killing vectors. The solution is stationary and axisymmetric. So that's the Kerr-Newman metric. And that's, in fact, all you can get for stationary black holes in dimension 4, unless you do something a bit exotic. They're specified by an M, an A, and a Q. are the most general asymptotically flat stationary black holes. In a certain sense, that's intuitively obvious. Suppose, for example, you had a black hole that had some higher multipole moment. Then, that higher multipole moment is going to get radiated away through gravitational radiation on a time scale of roughly that time it takes to cross the event horizon with light. So, higher multipole moments than just what you find in Kerr typically will be radiated away. But you might ask, could you find fields sitting outside the black hole in the same way that you find the electromagnetic field and give rise to extra degrees of freedom of the black hole? And the answer is essentially no. We will prove that in the next lecture, or at least we'll prove a special case in the next lecture. But this statement is really at the center of many interesting issues in gravitation. So this is summarized by the general title of uniqueness theorems, of which the most primitive one is Birkhoff's theorem that we saw right at the beginning of the previous lecture. So I think that's probably a good place to stop for today. Thank you.
Thank you very much for your lecture, Professor. It is this question is related to the instability of the inner horizon. Is the instability related to the loss of the Cauchy problem inside of the horizon, or
sorry, could you repeat that more slowly, please?
Sorry?
Could you repeat your question more slowly?
Yes. Is the instability related to the loss of the Cauchy problem inside of the horizon?
Oh,
or
yes.
Is related to the energy momentum tensor that explode at the horizon?
Let me see. Do we have any of those pictures left? I think the answer is yes. No. So let's suppose that in this picture you construct a Cauchy surface here. Let's use yellow so we don't get confused. And you ask yourself, what can you predict? Well, the answer is that you can really only predict what's in this region. If you ask yourself, what happens here, then the answer is that it will be influenced by what happens here. On the other hand, if you're talking about a situation in which there's gravitational collapse, the situation is a bit different, and I will deal with that in the next lecture. But the answer is yes. Typically, it's the inner horizon that gives rise to a problem with Cauchy predictability.
Okay, I see. Thank you.